All right. So, yeah, like I said, today we have a lot to get through. I was really hoping to wrap up the beginning part today, but I'm afraid that it might have to take up some of our next lecture. Um, but certainly after this week, we will be done with the first part of this class on background, foundation, all this kind of stuff. So far we've been talking about data structures and algorithms. We've discussed two data structures, arrays and trees, and we've discussed two search algorithms, um, linear search and binary search. Last class, we were going in more in depth into binary trees and trying to think about how you can take a binary tree and store it inside of an array. The reason why we care about this is because hardware behaves like an array. So in some ways, we're just stuck with arrays. At the same time, there's other data structures that look different than arrays that are really beneficial. And so if we can somehow kind of combine the two. Oh, I'm sorry. Okay, yep, sorry, mixing up the other class. That's due tomorrow for the other class. Apologies. All right, so okay, so we're trying to think about how to store different types of data structures. Right now, we're just talking about a binary tree inside of an array. There's two ways of doing it. The first way, which is a bit easier, and I'm going to kind of move quickly through it, because the next way is going to motivate some later data structures. So one way of doing it is you can take a binary tree, like on the left, and you can store it layer by layer in the array. So the root goes at the beginning of the array, and then the second layer, in this case 6 and 15, go next to the root in order. So it's first, or layer 0, layer 1, and then after that you put layer 2, which in this case is 5, 7, 12, 16. And because this is a 4-layer tree, we're going to encode the fourth layer. Because these values are empty in the leaves, then we put a null value in the array. All right, so this is one way of taking a binary tree and encoding it as an array. Yeah, that's not quite where I want to get to. Okay, so this is an important, I'll skip it for now. Are there any questions about this? The idea of taking a tree and representing a tree with an array? No questions, okay. Oh, is there? No, not quite. All right, so the last class we left off here talking about how to take actual data and store it as a tree. Because what we really care about in databases is storing real data. I mean, this isn't just one number that we're storing and it's nice and easy. It's an entire record. You know, it's a row of a table, if you like. So now on the screen is one way of making that idea fit the idea of a tree. That is to take rows of data, and how do you store, instead of rows of data in like a table, how would you translate that into a tree? Because a tree, especially if it's a balanced binary tree, you can get very quickly from the top to the bottom, log n steps maximum, which is very fast. That's the longest it would take you to find any entry in your potentially very long list of rows and rows and rows of data. You can jump to a particular row very quickly, searching for the row that you care about if you use a tree. So we'll come back to this, and there's some more detail that we have to fit in. But in any case, I wanted to give sort of a preview of that to ground where this stuff is going. All right. Just for something to percolate in the back of your mind, the tree, the thing that we use to find which row, let's say we have a bunch of data, okay, and we're storing it in a big, big, big table. And so each row of this table is one piece of information. Student ID, name, year, address, phone number, all of those things make up one entry, one row of this table. And then we have, I don't know, 20,000 students. So the table is 20,000 long. If we're searching for a student, then we want to be able to do so quickly. And you can break apart these two things. You can break apart the big, long list of all the student data that you have. And separately, you can have a tree. And this tree, you're going to use to jump to different areas in this big, long list of data that you have. So the little tiny tree, and you don't have to store all of the information in this table. You only need to store a little bit of information from this table. And so using like one column of this table, using just that one column, you create a tree. And it's this tree that's going to allow you to jump to different rows. So you take up a little bit more space. You have your gigantic table that takes up lots and lots and lots of space. And then you spend some time and a little bit of extra space to create a tree that is going to allow you to navigate this gigantic table quickly. That is called an index. Okay, so quick aside. I'm kind of previewing something called an index. So an index is like an index in a book, right? Here. Here's a book, right? It's got a whole bunch of information in it, right? I mean, it's like a big, thick book. But at the end of this book is a subject index, all right? And the index is 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12 pages. So this subject index at the end of the book is 12 pages, very, very small. Now, it takes up a few more extra pages than if you didn't have the index, but the index here is 12 pages versus the book's contents. So a database works the same way. You have all of this huge amount of data that you have, but you're not going to look through, from the beginning to end, all of your data. Like that would take forever. Instead, you go to the index, and if you know what you're looking for, then you'll have a page number that you can flip to, and that way you don't have to start at the beginning and go page by page by page by page, right? So that is where the jargon comes from. And the way that databases work, you have like a gigantic amount of data, and then you want to create a little index. Takes time to create the index. It takes a little bit of space to have the index, a little bit more than just the thing itself, but it helps you search faster, so it's worth it. All right. So that was my quick aside last time where we left off, and we'll get deeper into that either at the end of this class or next class. Like I said, I'm sorry, I think that to the level of detail that I want to get into, I think we're not going to be able to finish today. Next class for sure. All right. All right. So, again, where are we? We're talking about data structures, an array, and a tree. In particular, a binary tree. Even better, a balanced binary tree. And assuming that you have a balanced binary tree, which looks like the tree on the right side of the screen, how do you take that tree and put it inside of an array? Because we care about it. So one way is what I'll call the layer by layer way, which is what we've talked about. Now I'm going to talk about a different way. I did. Yes, it's been recording for like 12 minutes. Yeah, so we're still going. Thank you for reminding me just in case. Right, so this is one way of doing it, all right? I like going through it because it's, I hope, simple and gets the idea across of how you can kind of mix together two data structures. But the next one is going to be easier to build upon for the later, slightly more difficult trees. So let me jump into it. What is another way of encoding a tree? In fact, let me just take the same tree as above. Why not? I mean, I already drew it. So we can compare. Copy. And here, paste. Paste. There we go. All right. So there's a tree. Cool. Now, let me turn off my video here. What is a different way that you can encode a tree inside of an array? And just for fun, before I tell you about the way that I want to introduce, maybe you have your own way. Maybe you've thought about it. Hey, you thought this was like a cool idea, and you came up with your own thing. Or maybe you can in the next 20 seconds. Anybody have a different idea? Not going layer by layer, but just some other way of storing a tree. Okay, so sometimes this is how people get famous. Min to max. Min to max. Let's, yeah, do you mind speaking more about that? Left subtree, right subtree. Yeah, somehow you'll have to try to describe these. I'd be interested in hearing them. Min to max. Yeah, Anthony, how would that look for this tree?
For this one, I would assume it would be in the first square it'd be six. Oh, I'm sorry, five, and then six, seven. So just going in numerical order.
Okay, 5, 6, 7, 10, 12, 15, 16. Okay, so we'll call that min max. All right. Oh, sorry, I forgot 17. All right. Janet, what would your way look like?
Um, so 10 would be the first one, and then like I don't know, everything in I guess this would only work for a finished array, but like everything in the left subtree kind of had like kind of level by level like we were discussing earlier, and then the right subtree. But yeah, I feel like there's a lot of problems with like inserting stuff, but I thought it might work if you're just searching, but yeah.
Okay, so you're saying something like, okay, start with the root. Then here you're going to encode the left subtree of the root,
Mm-hmm.
and then you're going to do the right subtree.
Mm-hmm.
This is completely valid. So then for the left subtree, look at it like its own little tree. So put the root there. And then for that root, you're going to have its left subtree and its right subtree. So it's first the left subtree here. This is now the left and the right subtree there. Well, that starts with a 5. And then the right subtree would start with a 7. And then it's the 5's left subtree is null. The 5's right subtree is null. The 7 left subtree is null. The 7's right subtree is null. All right, and now we're on to the right subtree, which has a root of 15, and then it has two subtrees, obviously the left and the right. The left subtree, so again, left, right, and maybe you guys can finish it from here. That is cool. Yep, that would work. That's totally consistent. You could totally do that. Everything would work. You'd still have, the same. You need to reserve space for the empty nodes, because you should keep track of the depth of the tree, and so like there's some nulls here, because the 5 and the 7, they don't have children, but the 16 does, and so you need to allocate a little bit more space. Yeah, all that works. Yep, that would be valid. So the second idea, left subtree, right subtree, is very good. Without going into detail, which I'd like to do, but this isn't necessarily that type of class. This method on the bottom, this is the same as the layer by layer. Right? It's a different approach, but all of the benefits, all of the negatives are identical. So the layer by layer way that we discussed before, and this way, doing a subtree thing, you could do one or the other. You get the same thing both ways, right? If you're interested, I leave that up to you as an exercise to show. If you send it to me, I don't know, I'll give you some extra credit and be very pleased with you. But I'm not going to go through it myself. I'll tell you as much that it works, and it has all of the same benefits and all of the same drawbacks as the layer by layer method. All right, the min max. This is different. This is different. The min max is not a tree, because from this, from this information, how do you reconstruct exactly that tree? There's not enough information to go from this array on the right to the tree on the left. For example, if I moved the 17 instead of putting it here, and then I made a bad binary tree and I put the 17 here, right? So this is a bad binary tree. But using this min-max approach, it would produce the exact same array. So there's one correct tree, and then there's one incorrect tree that would both be represented by the same array, which means that from that array, there's no way to recover the tree. So that's different. It is a way that you can sort your data, and it has some benefits, like you can do a binary search because it's sorted, but it is not a tree. It's something else. It's just sorted data. It's sorting your data in an array. For a tree, when we say that you encode a tree, then that means that there's certain rules that you follow, making a tree into an array. And now, if I take away the tree and you have the array left, from the array alone can you build the tree exactly as it was. You're not going to have two different trees that make it, because then you don't know how to take the array and create the tree. You can't take an array and have it create two different trees. Not cool. One tree can encode in one way in the array. Therefore, going from the array back to the tree, there's only one way to do it. So, okay, very good. Both good thoughts. And especially, yeah, the left subtree, right subtree. That's very clever. And it works. Yeah, if you were, 3 months ahead of the layer by layer guy, you would have beat him out. Or if you guys came out at the same time, you would share the name. Oh, questions about that before I move on? No. All right. Yeah, this class I'm going to move a little bit faster. I don't know if most of you guys feel like that the pacing has been good or slow or fast. If you feel like that the pacing has been fast, this class is going to be a little bit more uncomfortable. If you've been keeping up, yeah, it'll just move a little bit faster. I don't know, take an extra sip of coffee. Okay, yeah, because we have stuff to get through. All right, so I'm going to explain the second method by first going through something that is review and might feel a little bit unrelated. But okay, turn that off. Let's go back to arrays. What I'm talking about now is a pointer. What is a pointer? So if you've studied certain programming languages, the idea of a pointer is very obvious to you, but I don't know what exactly people's background is. So I'm going to quickly explain the idea of a pointer, because it's not difficult. Let's take an array. Any array, I don't know. 5 minus 10, 20, 30, 124, okay? It's an array with numbers. This array has indexes, okay? So that if this is array A, then A of 2 would be 20. All right, so through Python, I think you guys are aware of this type of thing where you index an array by the index. I mean, this is called the index. Okay. If I've any questions about this much? No. All right. Now, I'm going to define a different array B. And B is going to be A sorted. So this should be the sorted A. But I'm not going to sort by the value. I'm going to sort by the index. So here, let's just sort by value first. That would be minus 10, 5, 20, 30, 124. And then B would also have its own index, right? So B, in this case, of 2, would also be 20. Okay, so right now, B is the sorted by value version of A. Okay, I've just reordered the values to make them sorted. No problem. But that's not exactly what I want B to be. What I want B to be is the, well, here, I'll call it C. Now I'm going to call it C. C, this is by value. C is going to be sorted A by index. So C is going to have the same indices, 0, 1, 2, 3, 4. But the values here are going to be pointers into A. So this value 10, which index is that in A? Okay, 1. Index 1 in A is the smallest value. Then for 1, now this is 0, because the second smallest value in A is at index 0 in A. Okay, 20 is 2, then 3, then 4. Okay. So, this is the thing that I want you to focus on internalizing. C itself has its own indexes, 1, 2, 3, 4, 0, 1, 2, 3, 4. But the values of C, 1, 0, 2, 3, 4, those values are indexes of a different array. Another way you could represent C, the array C, with indexes 0, 1, 2, 3, 4. So this is a pointer array. Okay, a pointer array. Another way that you could do this is like this with pointers. So then this would point to 1. This would point to 0. This would point to 2. This would point to 3. And this would point to 4. Okay, so the C here on the left and this C on the right, these are the same C. I'm just drawing them 2 different ways. Okay, one, I'm using arrows to point to what it means. The other, I'm just using numbers to say the index that I'm talking about. All right. Let me pause, because this is an important thing to wrap your head around. If you're uncomfortable with this, bring it up now, because we're going to be building on top of this idea. So if you don't get it now, it will be worse later. please ask if you have questions, or I can do another example or something.
Could you do one more example about this?
Sure. So let's see. Let me stop this over here. Okay. Let's do another example. Two pointers. All right. I'm going to draw this a little bit differently. I'll say A is this. 5, 8, minus 1, 2, 4. And John, Mary, Jane, Chris, and Fritz. And whatever. So it's male, female, female, male. All right. Whatever. So we have this. Okay, so this is our array A. And this is going to be indexed in this way. Okay, row by row. Okay, so hopefully it's not too big of a jump. Instead of a number, we're having a row. All right, so it's still an array. This array still has 5 indexes altogether. I'm just writing it a little bit differently. Now, let's create 2 arrays. I'll call this one by num, and I'll call this one by name. Okay, now these are going to be index arrays. Okay, so let's start with this one. All right, we'll fill out this one by num. And so what this array is going to be is this is an array of A sorted by num. Num, name, sex. Okay, let me pick on somebody. Let's see, B2, I refer to the 20 because of array A. So C2, right? C2 equals 2, which implies that A of 2 is the third smallest number. At the third, in A. Okay, so C2 equaling 2, that means that at position 2 in array A is the second smallest, the third smallest, because we start at index 0, is the third smallest value in A. So this isn't that hard. You just need, it's a simple concept, but maybe, a little bit of practice to wrap your head around it. So let's continue. Let me pick on somebody. Time to pick on people. That's fun. Where are participants? All right. How about Evan?
Hello.
Hello. So this binum array, I want to store the index of A such that binum is sorted from low to high, let's say. Does that make sense?
By the value of the num column, right?
Correct. Yeah.
Okay. Yep.
Okay. So what would binum look like?
It would start with -1.
Do I write -1?
Would it be its position?
Yeah, its position. Let's do that.
So it would be 2.
Uh-huh. Okay, and then?
2, 3, 4, 0. lost count. 1.
Very good. Perfect. Excellent. All right, great. Thank you very much. By the way, whenever I'm asking about arrays for pointers, you can do it like this with the numbers, like we just did. You can also do it by these arrows. If you like the arrows better, whatever, I don't care. They're pointers, okay? These are two different representations. Some people prefer one over the other. Maybe it depends on the circumstance. Whatever, I don't care. Arrows or indexes, it's fine. Okay, now let's pick on somebody else for the by name. So we have the by name. And now we're going to be focusing on this one. How do we sort this by name? How about Krutika or Krutika?
Hi.
Hey, I'm sorry, how do you say your name?
Yeah, Kritika. Fine.
Krutika, great.
Mhm.
So, we want to sort, or we want this array by name to be the index of A such that the name column would be alphabetically sorted. Make sense?
Okay.
All right. So
You would have 3.
3, very good. Yeah, because Chris, C is the lowest letter of the alphabet. So that one goes in position 0, and that is index 3. Okay?
Then you would have 4.
4. Okay, yeah, because F is the next. So that's 4.
And
Okay.
then 2 with Jane.
Yep.
And then 0 and 1.
0 and 1. Perfect. Excellent. Very good. Very good.
Okay.
So that's it. That's the idea of pointers. Okay. These numbers here are indexes to another array. And these indexes should be interpreted as being sorted by the thing that we care about. So in this array, we care about things being sorted by name, by the name column. And in this array, by num, we care about things being sorted in the num column. All right? So the by num array is different than the by name array because numbers are different than names, and I mean, hopefully this is self-explanatory now. Okay, very good. So that's it. That's it for pointers. Pointers are used a lot in computer things, but now you know about them. All right.
I'll just call her. Don't call her.
Sorry, I hear some background noise. I'm not sure if that's a question or if it's.
Make sure it's okay. What do you want? Jelly or jam? Nothing. Do you want butter? No. I'm gonna get that too after.
Sorry, I guess I'm going through muting everybody. We'll get to it. All right, here we go. Okay. Very nice. Okay. No problem, no problem. All right. Yeah, I thought that I had everybody mute on entry, but I don't know if I can set that up. Okay, great. Now, God, good. We have 40 minutes left. We're making okay time. Okay, so that's a big idea that we're going to be building on top of, this idea of pointers. There's not much more to say about it other than I already have, or as much as I've already said. That is it, pretty much. So, great. Now, let's talk about this second method. I'll take this here. Now we have everything we need. We cut that, and I'll put it down here. Now we're in method 2. Well, actually, actually, you know what? Before, I'll give it. But what I will say is that up here, we talked about storing a tree as an array, layer by layer. The whole reason why I'm talking about pointers is because there's a different way that you can encode a tree in an array using pointers. So, I won't take too long, but I'll give you guys a minute or 2 minutes. Play around. Okay, I'm telling you that there is a way to store this tree inside of an array with pointers. Long story short, and this should maybe give you enough to work on, we're going to store 10 at the beginning, just as always. But this 10 is going to have some baggage. Okay? Maybe it's 1 or 2 or 3, whatever. There's going to be some extra stuff for the 10. And then we're also going to store the 6 and the 15 and the 6 and the 15. The order here doesn't matter. But each node by itself, we're going to be storing as a block in here somewhere. And each of these blocks are going to point to other blocks. They're going to have the value of the node. Sorry. So here, the 10, that block, this block needs to have the value 10. Here's a different block with the 15, let's say. So this block for 15 has to have the number 15. But in addition to that, it's going to have some extra stuff, which are pointers. So let me give you 2 minutes to see if you can fill in the rest of the puzzle. I'll mute and give you guys time to work on that. Okay, any ideas? 10, 1, 6. Okay, hold on. 10, 1, 6, 2, 15, 3. Okay, can you help me explain, or can you help explain what these are? What this means?
I'm guessing 10 is the first one, so the number next to 10 is its index, and 6 is the second number we put in. So the second is index.
Okay, so you're saying that there's some other array. Let me not write those numbers. Let me instead do it as a pointer. So here's another array, 0, 1. And so this is a pointer to position 1 in some array. This is position 2 in some array. Here we have position 3 in some array.
They start from 0.
Come again?
Maybe I should start from 0 but not 1, like 10, 0, 6, 1, 15, 2. Yes.
And yeah, not quite. Yeah, this is sort of the order, but the order doesn't. Okay, hold on. So what if I put instead of 15, just out of curiosity, what if I put the number 17 here? Where does that pointer go?
Have no idea.
Okay, good. Well, cool. Yeah. Hey, that's well, it's an idea. Not bad. All right. Any other ideas? No. All right. Well, good. I hope that the time working on it was fun. Of course. How could it not be? All right. So this is while the other one I call it layer by layer. This one I'll call it node children pointers. Okay. So let me redraw this a little bit. Just get rid of these. And one cool thing about this is, remember, in the layer by layer, the positions really mattered, right? I mean, anything in this section of the array, that's the second layer, right? It has to be the second layer. So there's a very tight connection between the position in the array and where that translates to in the tree. It's in this way that we can be given any array. And notice, if I give you this array, you can build this tree exactly. All right. But one property of that is because it's layer by layer, you might need to waste some space when you have an empty layer or a mostly empty layer. All right. Now, pointers don't have to be pointers to a different array like we were doing here, right? Here, this pointer is to a different array, 2, 0, 1. All right, so this array is a collection of pointers to a different array, A. We're going to modify this a bit, and this is actually going to be a pointer to itself. And so here's the generic block, okay, for each node. Each node. So it's going to have the value, and then it's going to have location of left child and location of right child. Yeah, give myself a little bit more room here. All right, so here, 1, 2, 3, 8. So just for fun, we'll start with 10. Then we'll have 2 extra nodes, okay? So this node is going to be represented in this way. We put the value, 10, at the front. And then here we're going to put the left child, and then here we're going to put the location of the right child. We'll get to that in a minute. Right now, we'll just leave 2 extra spaces. Now, let's say, I don't know, because this is our second node, 16. And then we have the node 17, and then 6, and then 15, and then extra stuff, okay? Now, 10. First we need the indexes on this array. So that's 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14. So if this is our array A, then for example, A of 12 is equal to 15. All right. A of 3, 16. Okay, so fine. All well and good. Now for 10, this node here, its left child is the number 6. 6 is at location 9. So here we can put the number 9. Or if you like, you can put a pointer there. That's where the left child is. Where's the right child? 15. Or otherwise at index 12. Okay, 16. 16 does not have a left child, so that's null. 16 does have a right child, 17, which is at that index, 6. 17 doesn't have any children, those are null. 6 has a left child and a right child, and those are somewhere else later in the array. 15 has a right child 16 at position 3, and a left child 12 somewhere else in the array. Ooh, all right, let me pause. All right, so that is the idea. That's it. So we're using, instead of layer by layer, we're doing it with value and pointers to children. I'm going to pause and ask 4 questions. I'll go through one other example of this. But before that, if there's any questions about what I've already done.
Hi, Professor. Just want to clarify. So these pointers are pointing to themselves in the same array, right?
Yeah, not pointing to themselves, but they're pointers to different locations in the same array.
Okay, all right. And then one more thing is, so the 10 to 16 to 17, all the node values, they can be in any order that they want, right? So
that's right.
10, 5, 7. Okay, great.
Yep.
Thank you.
Yeah, very good, very good. Yeah, and that's a big benefit to this. It's a benefit because, again, order doesn't matter here. You insert a node. Remember, like, why was linear search insertion so fast? Because the order doesn't matter. Throw the thing at the end. That's order 1. You do it in an instant. And it doesn't matter because everything is unsorted. In the same way, in this way, insertion into the tree is order 1. You just throw it at the end, and then you update your pointers. So it's actually it's not. It's actually log n, but in any case, it has the same type of property where you can just, if you're inserting a new value, you just throw it somewhere. The same thing, if you delete a value, you just update your pointers. And then like that's a little bit of empty space. And then you can fill it up. The next time you insert a node, great, insert it in that empty space, no problem. But the order doesn't matter here. Why is 10 before 16? And why is 16 in between 10 and 17? Doesn't matter. Because the location in the array isn't important. Because the pointers, you can have the pointers go anywhere you want in the array. So it's like referencing in code, a little bit like that, yeah. And you just update, where things point. So you can throw things in, you can delete things, and just keep everything in place. You don't need to shuffle things around. So this is great. This is kind of mixing the both of two different best worlds. You have a tree. Everything works like a tree. You're encoding it in an array, and a part of that's by necessity. Again, because, all this stuff is actually ending up on hardware at some point, and so it just has to be an array. But good news, you don't have to lose anything. You can have a tree in an array, no problem. It's just when you look at the array, you have to interpret it in a particular way. And if you interpret this sequence of numbers in a way where it's value, location of left child, location of right child, and you do that for the whole thing, then great. Now you're not looking at just a random string of digits. You can map that string to construct a unique tree. I can give you an array, you can build a tree from it. And that's all we need. That's it.
I have a question.
Mm-hmm.
For like position 3, how'd you put 16 in there? Did you just like randomly assign?
Yep, randomly, doesn't matter.
Okay. So basically the pattern here is like putting the root in and then leaving space for 2 leaves and then like the next root you want to do.
So you put in whatever the first node is. Okay, let's see. In this case, the root does not have to be at the beginning. That's an accident. This is why I put the root and then 16, 17 to emphasize that the order is nonsense here. It doesn't matter. It can be whatever you want. Because you have the pointers that will correct all of the left children, right children. Now, you do need to know where the root starts, but the root doesn't have to be at the beginning of the array. You just have to remember where the root starts. And so, like, that's an extra, whatever. You store whatever the location of the root is right now. Why do you need that?
Could you have put the 16 in like 1? No, right?
Okay, let me do it this way. I'll draw something simple and then I'll pick on a student. How about that? All right, same tree. All right, same tree, different array. All right. Now, the actual order, sorry, let me say this real quick. The actual order, like why did 10 come first? Why did 16 come second? Why did 17 come third? It's because we inserted 10 first, and then we inserted 16, and then we inserted 17, but there was no rhyme or reason to what order we were inserting things at. We were just throwing them in. I happened to get this at that time, so I put it at the end, and then I happened to get this thing next, and so I put that there, and on and on. So let's build the same tree. We'll build it from scratch. And then we'll just see what kind of array we get, and we'll compare the two. All right? So, but we didn't really cover in depth how to reorganize trees. That's too much for this class. Yeah, that's too much. That's too much for this class. I'll do something in between. So let me put 7 and I don't know, 15 and 6 goes. I don't care. 17. Why not? I'm just choosing random numbers. 10. What haven't I used? 5, 6. Do I have 7? I do. 12. All right, whatever. Okay, there we go. Different order of nodes. And just to make things easy. Okay, there. Now I've just labeled the indexes of this array. I'm going to call it A prime. Okay. So after each number you put in, there has to be 2 spaces to store the indexes of its children. Yes. Oh, I'm sorry. No, I don't need 6 twice. So I've got 10. I've got 6. No, I've got 15. 5, 7, 12, 16. Haha. There you go. I don't have 16. I'm not going to do a 16. All right. I know I'm still missing 17. Whatever. Okay. Yes. So we have 2 spaces because this is a binary tree. So there is at most a left child and a right child. If we were dealing with a trinary tree like this, then it would be value, location of left child, location of middle child, and location of right child. So the reason why we have 2 extra spaces here is because we're dealing with a binary tree. If you're dealing with a tree with 3 children, then you need, another location for the 3rd child. So yes, in this case, we do need 2. No, it's not special because you can have trees with more than 2 children. But for however many children the tree has, so this above is called a 2 tree or a binary tree. This would be a 3 tree because you can have 3 children. And so for an M tree, here you would have M different locations. 4, 5, 6, 10, 1,000, whatever it is. However many children you have, that's how many extra locations you need. Plus 1 for the value. Oh, you don't need a middle location in a binary tree. This is a 3 tree. This is a trinary tree. This is a binary tree. So binary is 2. So that's a 2 tree. A trinary tree would have 3. So I'm just giving an example. We're not talking now about trinary trees. We're talking about binary trees because they're a little bit simpler. But if you understand it, here, look, if you understand a binary tree, you could do this. You could add a 3rd thing because you have 3 nodes and fine. What if it has 5 nodes for children? What if you have 5 children? Well, then you can just make the thing with 5. Like if you understand 2, then you can make any other number you like. So I'm focusing on 2 now. We'll focus actually a little bit more on the 3 next class, probably. We're going a bit slow here. All right. Get rid of all that. Cool. All right. So for this binary tree, or for this A prime, right? We're focusing on A prime now. And the point of this is that here, this one, this is one way of doing it. All right. I'm trying to emphasize the fact that 10 coming first, and then 16, then 17, then 6, that doesn't matter. That's an accident. Okay? The order here, you can make it whatever order you want. Shuffle it around. And it doesn't matter because the pointers are all going to point to the correct places. So, as an example of that, I'm giving a different order to things here, and we're going to see that everything will still work. Okay, we can still encode the exact same tree, we're just going to be encoding it in a different array. But each of these arrays can uniquely reconstruct this tree. So for this encoding, you can have a tree, and you can have multiple different arrays that are all equal, where each of these arrays can uniquely rebuild the tree. So you're not going to have one array that could build two different trees. That's a problem. You can have one tree build multiple different arrays. That's fine. But it's going back the other way that we care about. When you encode A as B, if you encode A as B, the important part about that is given B, can you get back to A? Now maybe A can go to B, A can go to B prime, A can go to B double prime. That is okay so long B goes to A, B prime goes to A, B double prime goes to A. This is the important part. Can you take an array and build one tree? Right? These aren't building different trees. They're all reconstructing the same tree. And it's this property that we care about. That's for encoding, right? This is here. Encode A as B. And you can have different Bs. Maybe they're a little bit different. Here's a concrete example of that. Here, if we call this tree A, and then this B, and then this B prime. Let me do it this way. This is tree T, this is array A, this is array A prime. So here, tree. The tree can be encoded as A or A prime. So we're going to have two different arrays. A is different because A starts with 10, A prime starts with 7. So already those two are different. But we want to make sure that A goes to T and A prime goes to T. We're already good that A here can go to T. Because we could start here with the first node 10, and its left child is at index 9, which is the number 6. And its right child is at index 12, which is the number 15. And then 15, here we can see, has a child at position 3, which is the number 16. 6, well, whatever. You can see that I can reconstruct this tree, right? I mean, I'm already on my way. This is starting to look like that. All right, let's go through this. Can you discuss the advantages and disadvantages of the second method versus first method? Yes, I will. Yes, I will. I'll explain that. After we go through this. Let me pick on, where did the 13 come from in the first array? 13. In the A1 array. Oh, A prime. I'm not seeing a 13 here. Seven, 15. That's a 15. Yeah, it's a 15, sorry. I know, I write my fives funny. 15. Okay. Now, okay, so here, A prime. We are encoding this tree here, right? We are encoding this tree inside of an array A prime. Just because, and it doesn't matter, you can put the nodes in whatever order you want, putting the 7 in front, followed by the 15, and then the 6, and then the 17, and the 10, because I was flipping a coin, right? No rhyme or reason, nothing important about it. Okay, how about Catherine?
Yes, can you hear me?
Mm-hmm.
Okay, so for 7, would it be null, null?
Very good, because 7 here has no children. So that would be null, null. Okay?
Okay, and then 15 would have 21 and then 18.
Very good. Perfect. All right. And the 6?
The 6 would have 15 and then 0.
Very good. Okay, well, you are knocking that out of the park. I'm going to pick on somebody else to see if I can finish us off. But yeah, perfect. I think you got it.
Okay.
How about Dev?
Yep.
Okay.
For 17, it would be null, null.
Yep.
Then for 10, it would be 6 and 3.
6 and 3. So, hold on, let me make sure. 10, 15. Yep. Okay.
And then for 5, it would be null, null.
Yep.
And for 16, it would be null, then 9. And for 12, it would be null, null.
Perfect. All right. Awesome. Excellent. Very good. So that is exactly how it's done. Okay? This is a different way of encoding a tree in an array. And this is the way that we'll actually be building more on top of. So I want you to feel very comfortable with this way. The idea of using pointers. So far, so good. I mean, yeah, it seems like you guys are doing great. Proud of you. Okay. There was a question. What are the advantages and the disadvantages of method 1 versus method 2? I will answer that, but before I do, any of you guys have thoughts? Level by level versus, I don't know, pointer. Let's do pros, cons, cons. Yeah. Any ideas?
So for the pointers, I think you mentioned this before, but like the order that you put the nodes in doesn't really matter because they're just like the location information will be there anyway, if that makes sense. It's like not dependent on the order of the array.
It does. Yeah, that's partly true. Yeah, that's so. Yeah, that's partly true. It turns out that actually these are both the same. Insertion time for both of these is log n. Actually, I should go through that very quickly. But it turns out these are the same. So I'll say here, log n search, log n insert, log n delete. Right? All of these have those properties. Same thing with the pointers. Here, you get the benefit of both. This is why we're encoding a tree. Keep in mind, remember, I'm not going to scroll back up to it, but when we were using the sorted array from like low number to high number, search was log n, insert time n for insert or delete, and same thing here. I mean, like for the sorted array from low number to high number, good search, log n, not bad. Big improvement over n, an exponential improvement, in fact. But yeah, insertion delete was slow. With both of these methods, oh boy, look at that. We get the insertion and deletion down to log n. I will justify that. I'm afraid we won't have enough time this class, but I'll start off with that next class. So this is actually a pro for both of these. It's a good reason why we're talking about it, right? Because trees are great. Super, super great. You can do log n search and delete, and that's fun.
Professor, just
Yep.
want to clarify.
Yep.
I'm kind of confused just on how the nodes are organized here. What's with the log n, right to the left of search, and then the log n to the right of search?
Right. So, okay. So I'll just add it here on a regular sorted array. So that is if you have an array like 0, 1, 2, 3, 4, 18, 20, whatever. If you sort your array from the lowest number and then the next, and it's just like all nice and sorted like this, then you get this thing on the right.
Got it. Okay. Thank you.
Right. Okay. Then, because we only have 2 minutes left, I'll just throw these out there. Let me turn this off real quick. All right. So in general, we're going to lean more heavily into this. All right, into using the pointers, because for our purposes, it will better lend itself to the actual kind of data structure called a B+ tree, and this is what we'll cover the next time, a B+ tree. You can go ahead and read about it if you like, or watch YouTube videos or whatever. I'll cover it from beginning the next class, but a B+ tree really comes more from this pointer idea. Okay, so that's why after this class, I'm basically going to be abandoning this level by level. I think that that's an easier introduction to making a tree and encoding it as an array, which is why I spent a class on it. Now, let's think about this for a minute. If you have a full binary tree, if you have a full binary tree, then this is the most space efficient. Okay? Because there's no space wasted at all. All right? So layer by layer by layer, that's how you're storing it. No pointers. You don't need extra space for the pointers. You're storing the values and nothing else. But where you store those values is how you rebuild the tree. So if it's a full tree, then this is very space efficient. You save a little bit of space, that's great. If you know you're dealing with trees that are basically full, sure, level by level will save you a little bit of space. Because not storing pointers. All right, cons. Cons. Now, what if you don't have a full binary tree? What if you have a tree that looks like this? All right, you're going to have a bunch of nulls. Not good for unbalanced trees. Right? Why? Because there's the level 1, then level 2, there's a null, and then you're going to have a null and a null and a null, and then your value. And here you're going to have a null and 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 a null, and then your value. So I mean, already, like if you keep this going, you're going to be taking up a bunch of space that's mostly null values. It's a big waste of space. On the other hand, the pointer tree is very, very space efficient for unbalanced trees. Good for unbalanced trees. Unbalanced trees. Cons. Uses more space for balanced trees. All right, so if you have a balanced tree, instead of, take this tree here, right, a fully balanced tree, while the layer by layer would take up 1 for the first node, 1 for the second, here's that layer, and then here's this layer, right? And that's it. That's all the space that we take up. 1, 2, 3, 4, 5, 6, 7. 7 for the layer by layer method. But for this balanced tree, if we're doing it in the pointer method, well, we'll have one node with its left and right child, and then we'll have another node with its left and right child, then we'll have another node with its left and right child, and we do that 7 times over because we have 7 nodes. Whatever it keeps going on. All right, something like this. So you'll notice, once you have, how much space does that take? Well, you have 7 nodes, each of which take up 3 spaces, so that's 21 spaces that you've taken up in the pointer way to represent this tree, where if you're doing it layer by layer, you're only taking up 7 spaces. So depending on if your tree is balanced or not, you might be able to save a little bit more space here or there, depending. That being said, being off by at most a factor of 3 isn't bad. And so for most of the time, you'll just do the pointer thing. Sometimes you might use up a little bit more space, but I mean, unless you're really hard pressed for space, yeah, just the node way works out. Okay, so that's it, guys. Yeah, sorry, we're past class. You can log off. We'll pick it up next class, and I'll hang around for a few more minutes if you guys have questions. Upload new recordings and we cover the new recording class of 921. The second one is of 914. Seems like we are missing 917. Okay, thank you for that. I will make a note. Look into that. Team class and repeat of (921). I thought I uploaded 924. So wait, is the 924 class missing as well? Because I thought I just uploaded that before this class. Okay, okay. Cool. Yeah, sure. Yeah, thank you for saying that. Maybe you can double check later. I'll check as well. Yeah. Sorry, I've been running into various computer issues over the past couple of days, including before this class, which is a lot of fun. I was starting up WebEx, and it said, bad security certificate from WebEx. You can still use it, but no audio and no video. Well, then, perfect. This class is going to go great. Anyway, yeah, luckily I figured that out beforehand.
Hi, Professor. I have a quick question.
Yeah.
when is the first test?
Oh, so the first midterm is going to be, let me think, we're going to be finishing up this week, probably next week, something like that. So,
Okay.
yeah.
Oh, because I'm trying to take like vacation days so I can like have like try to study before for my job. So I would appreciate like if you like know like the exact date so I can request off.
Sure. Don't let this class's midterm get in the way of your travels. I would love to give you the midterm. In fact, I'll release the midterm in a couple of weeks. I think that the midterm is not really going to include any more information than the first part of this class. So
Okay.
that's going to be all of this background stuff. Next week, we'll be starting on ER diagrams, and I'll put out some type of review, but yeah, the midterm won't include any of that. That being said, yeah, if you book your departure earlier, I'd be happy to give you the midterm earlier, and you can have it done and finished and not worry about it as you're exploring the wide world. And yeah.
Oh, I'm not going anywhere, Professor. I'm just requesting a vacation day so I can study like at home, like so that way I don't have to like work.
Oh, I see.
And
Okay.
I have an extra day to study. Yeah. I
Okay.
wish I was going somewhere.
Okay, sorry, I misunderstood.
No, it's
Yeah.
okay.
I was going to say, how are you getting out of this country? Because I thought we're blocked from like anywhere. Yeah. Okay. So yeah, I would say it's either going to be next Tuesday or next Thursday that it will be assigned, and then you'll have a little over 24 hours, more like 36, to go through it. It should really only take you maybe an hour and a half, maybe. But yeah, you have plenty of time to work on it. But yeah, sometime next week, I'll release it. If you want me to release it for you a little bit earlier or something, let me know. But yeah, I'll give everybody a better timeline. Certainly next week. I'm not sure next Tuesday or next Thursday or next Monday or next Thursday. One of those two.
Okay, Professor. Thank you so much.
Yep. All right. Have a good one. Oh, what was the extra credit that I was talking about? Yeah. Yes. This. What was it? Somebody was saying the layer by layer, and somebody said left subtree, right subtree. Dang, did I delete that? I think I did. So, we talked about how to encode a tree layer by layer. There was another student who said a different way of encoding it would be left subtree, right subtree. And that works. Like, totally. Like, that's a completely valid way of encoding a tree. In fact, it was the first time that I had heard of it, which is why I asked. Like, that's great. Perfect. Like, that's a really cool idea, and it works. The extra credit would be showing that encoding something layer by layer and encoding something left subtree, right subtree, that those are actually the same thing. They will, in all of their benefits and negatives, for all their pros and cons, they're the same. So here, when I'm saying here on the left, the pros, login search, login insert, login delete, and it's the most space efficient for full trees, all of those things identical, and the same thing not good for unbalanced trees. The amount of space that the layer by layer method would take up is identical to the amount of space that this left subtree, right subtree idea would take. So they're two different approaches, but they're in all of their pros, all of their cons, in the ways, in the performance of them, that would be like one-to-one identical. And if you can show that, hey, that's really cool. It wouldn't take too much, but yeah, you need to sit down and think and draw a couple diagrams and stuff. So that's it. Make sense?
So you just want us to like draw like both of them out for like a sample like binary tree basically?
Yeah. So just think about a binary tree, and you know, you can give a couple demonstrative examples.
Mm-hmm.
So this is maybe a good case for a layer by layer, and this is a bad case for a layer by layer. If you do layer by layer, this is the resulting array that you would get, and then you can count the length of the array that you need. You know, like what's the length of the array that you need for these, and then you do it subtree subtree, and then you show that the arrays, their lengths are exactly the same.
Okay.
And that's basically it. Yeah, I'm not asking for a very formal proof, although, yeah, I mean, if people show interest in this kind of thing, I mean, I'd be happy to push more along that direction on the side. But yeah, for this class, that's pushing the boundaries of what I would expect people to do. So extra credit. Yeah.
All right, cool. Thank you, Professor.
Yep, no problem. Have a good one.
Have a good one.